Oh, it worked. We're going to do word problems, so this probably shouldn't take us too long. There's a good chance you get a word problem on your diploma exam. Sometimes they put them in funny formats, so I think like the next one has that like funny format for a word problem, and I'll show you how to handle those. But we'll start with this one where the formatting is pretty easy. It's already done for you. Oh my goodness, this is going to be a struggle, but we're going to get through it. Okay. Yeah, I know, right? So the first thing with a word problem is I would try to obviously read so you understand what's going on, but try to pick out what it's asking for, because sometimes that can be the trick to the question. So it says, when there's no wind, a runner is able to run 10,000 meters at an average speed of X meters per second. When he runs with a tailwind, that means there's a wind at his back, it's like pushing him, his average speed increases by 0.05 meters per second, and it takes him 15 seconds less to run the 10,000 meters. The equation shown below represents this relationship. So this is a word problem where they give you the equation. So it's actually kind of nice. At the end of the day, if you just solve the equation, it's probably the answer, like in all honesty. But it's still wise to highlight what it is they want. And the question was nothing. There was no question. That's great. It never asked the question. It's just a statement. Here's the equation. Boom. Who made these notes, Mr. Kennedy? We'll pretend the question is here. How fast? Oh, this is not going to be good, people. Does he? Is this a he? Yeah, it's a he. Run. Oh my gosh, I lost my stylus and this is awful. Okay, give me a second. All right. Now the YouTube video, if people watch this, they're just going to hear me heavy breathe for the next hour. They're going to be like, I can't understand what he's doing because he's breathing so heavily. How fast does he run? That's the new question, if you can't read what that says. In the question, they also should define any variables, which they did. Right there, underlined in green. They told you that X was the average speed. So that's the speed that he's running at. So all you have to do for this problem is solve the equation. They did throw something in. When you look at this equation, this right here sometimes freaks people out. So that's a restriction, right? We've talked about that before. A restriction is just defining the variable for possible values. So what they did there is they said X had to be greater than 0, which makes sense. X is the speed that he's running. He has to be running a speed, right? So it has to be a positive speed and it has to be bigger than 0. Otherwise, he's not moving or he's going backwards. I don't know how that works. That's all that means. It actually has no effect on how you do the question. So you could pretty much just ignore it. They put it in to make that equation more mathematically sound. That's all. The real equation is this guy that I'm highlighting in red. That's what you have to solve. Cool. Solving it. When I want to solve an equation, I follow my 3 steps. First step to solving any equation is factor. I can't factor that, but what I can do is I can put brackets around any binomials I have, which might help me in the future when I get to step 3. The second thing I should do is state my non-permissible values. It doesn't ask for that, but just for good habit, we'll state it. The non-permissible values is x cannot equal 0 or negative 0.05. Both of those things would cause you to divide by 0, which aren't acceptable. Now you're on to the third step, which is solve or simplify, depending on the question. This one would be a solve situation. To solve, what's the first thing you need to get? A common denominator. Perfect. That's where putting the brackets might help you. On this question in particular, the big thing I see people do when it comes to word problems, they kind of forget how common denominators work. And they say, oh, I need to get a plus 0.05 into both equations, which is actually wrong. You don't need to get a 0.05. You need to get this entire binomial into all of your equations, right? Remember, that's a package. So it means every fraction needs to have that package. That means the first fraction I need to multiply by x plus 0.05. And what I do to the bottom, I have to do to the top. Okay, that's one major mistake people make. They forget the packages. The second major mistake people make is the number 15 is actually a fraction, and it also needs a common denominator. That's 15 divided by 1. That means we need to give that thing a common denominator of x plus 0.05. That's probably the number one mistake that people make. They forget that that 15 over there needs a common denominator. I think if you forgot that, yeah, it's okay. You're just dying slowly. I understand. Yeah, right? I think what people it's all good. It's all good. I get it. I think if you didn't do that part, I think you actually ended up losing almost the entire question. So that is like a very important step. Like it was a written response, and he was out of 2 marks. And I think if you forgot to do the right side, the 15 over 1, it was basically like a write-off for the whole question. It might have been you could get a half mark still if you did something else proper. But it was a significant error in their mind. So please make sure if you get a problem like that, whole numbers are fractions, and they also need common denominators. Okay, there's something else I'm still missing in my denominator. X, right? That monomial x needs to be on every single fraction. So that means I need to give it to this guy right here, and what I do to the bottom, I do to the top. And I need to do it to the 15 as well. And what I do to the bottom, I do to the top. Unfortunately, I forgot to write the x plus 0.05 on the top. I now have a common denominator. It looks a little bit messy. I'm going to write it out just because I'll take the time to show you what we have now. So on the top, we have 10,000 times x plus 0.05. On the bottom, we have x times x plus 0.05. The second fraction is now 10,000 times x divided by x plus 0.05 equals 15 times x plus 0.05 divided by x times x plus 0.05. So you should be able to see now that I've kind of rewritten it, what our common denominator is, and that I've done it to the top and the bottom to every question. That's the first step to solving. Get a common denominator. Once you've done that, there's a trick that we know, which makes this a very handy question to solve. What's that trick? Cross the bottom out. You can't just do that when you have a common denominator, though. You have to have a common denominator and an equal sign. So please, please, please remember that. Don't be the person who does addition and then you're crossing out the denominator because you got a common denominator. That's only for when there's an equal sign present, that I can take all the denominators and erase them so that I only have the tops left. Now my goal, because I've gotten rid of my fractions, is to solve whatever equation I have. And this is a messy looking equation. The first step to solving is expanding. So the first thing I would do is multiply this 10,000 into the brackets. When you do that, you get 10,000x plus 10,000 times 0.5, which is going to be 500. Someone try it. 500. I'm putting it down with the most confidence I've ever had. Hey, basically a mathematician. The second one, make sure that you understand there's a negative sign right there. So it's still going to be minus, and then 10,000x. Had that been like a binomial or something, remember the negative would go in the brackets. Because there was no brackets on that second fraction, it just goes to whatever term's there. Equals. I have 15 times x plus 0.05. This is the same thing as saying 15x. So I can just multiply 15x into the brackets. So it's 15x squared plus that one I'm not as confident in. 0.75x. Yeah. I'm like Rain Man right now. You guys know who Rain Man is? That's okay. I'm old. Rain Man, go watch it. Rain Man? Oh, he is? Oh, yeah? Huh? Oh, no, 0 people. That's cool. I just make references that nobody gets. Once you've expanded, you should be able to tell the type of equation you have. There's 2 options. You have a linear equation, meaning the highest exponent is 1, or you have a quadratic equation, meaning the highest exponent is 2. If you have a higher exponent than 2, you likely made a mistake if it's a rational expression question. You might still be able to solve it. So maybe you have x to the power 3s and they'll cancel out or something like that. But what's more likely that happened is you didn't simplify along the way, or you did too many multiplications somewhere. Right? Like you did a common denominator that was too big. You could have done a smaller one. In this case, what type of question do we have? Linear or quadratic? Quadratic, right? Highest exponent is 2. To solve quadratics, we move everything to one side. I'm going to move everything to the right side. So that means I need to move these 3 things. Before I even move them, I'm going to recognize these 10,000 x's cancel out. One's positive 10,000 x, one's negative 10,000 x. They just cancel each other out. So the only thing I have to move is the 500. So I subtract 500 from both sides, which gives me 0 equals 15x squared plus 0.75x minus 500. To solve a quadratic, you have 2 options. Option 1 is factor. That thing would be a nightmare to try to factor, mainly because of the decimal in the middle and the really large numbers. Your second option is to use the quadratic formula. I do want to warn you that if you use the quadratic formula, you must show your work. So you have to write at least one of the steps of the quadratic formula on your piece of paper so that they know what you did. If you just magically appear with an answer because you did it in your calculator, they won't give you marks for it. You must show what you did. This is definitely a quad formula question. The way the quad formula works is when you're in this form, which is called general form, you have 3 values. You have an a value, which is in front of the x squared, a b value, which is in front of your x, and a c value, which is all by itself. A in this case equals 15. B in this case equals 0.75. C in this case equals negative 500. And those values go into your quadratic formula, which is negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. That formula is on your formula sheet, bottom left-hand corner, so you don't need to memorize it. I'm going to replace all those letters with numbers. I'm going to slide over here to the right side a little bit. Slide to the right. Doing this quad formula, that means x equals negative b. So negative bracket 0.75 plus or minus the square root of b squared. So bracket 0.75 squared minus 4 times a, which is 15, times c, which is negative 500. Notice that I'm putting brackets around everything. Those brackets could be very important, especially when you're calculating in your calculator. especially the squared part would matter. And then on the bottom, I have 2 times a, which is 2 times 15. If you were here yesterday, I told you there's 3 areas that I calculate before I actually calculate anything. So the first area I calculate is this guy right here. If there's 2 negatives there, I turn it to a positive. If there's 1 negative there, I leave it as a negative. So in this case, it's negative 0.75. It's the first thing I calculate. Then I have plus, minus, square root. And the second part I calculate is this thing, which is called the radicand, technically, or the discriminant, like the number underneath the root sign. But I'm just going to throw that whole thing in my calculator with brackets. I cannot do that one in my head. Rain Man could. Has anyone thrown that in there? So you do it without the square root sign, just the stuff under it. I just want a number. Yeah, the number that goes under the root sign. 30,000? Oh, sorry, I talked. 30,000 point. 30,000.5625. Like that? People got that? All right. Even if other people didn't get that, I was going to trust Cole because he's the smartest one in the class. And then on the bottom is the third one I would do, which is 2 times 15. That's 30. And honestly, I do, when I do these calculations, I break it up like that. It's a little easier to now put in my calculator than trying to do one whole thing. Remember that the quadratic formula breaks into 2 situations. Situation 1 is when you're adding. So I would have negative 0.75 plus the square root of that number. And then divided by 30. The other one is negative. So if I had 0.75, come on, computer. Minus the square root of 30,000. 0.5625. And you do have to calculate both. Even for a word problem, you must find what both equal. And if one of them is an unacceptable answer, you write it, but then you cross it out. So my guess is that the second answer won't be an acceptable answer. That's purely just a guess at this point. I'm going to calculate both. Has anybody done both? Has anyone done the top one? I should just grab my calculator. Oh, yeah, CV. What is it, babe?
Oh, I don't know all the decimals because I rounded.
That's okay. You can round it for me.
5.75.
5.75. Okay. And what's the second one? Negative 5.75. That's convenient. The negative answer is unacceptable. Why would it's not an NPV, but why would it be an unacceptable answer? You can't run negative, right? Remember that we were solving for x. X represented the speed they were running. Can't run negative 5.75. So that answer I write and then I cross it out. The other answer I write and I put a box around it. Even better for a word problem, maybe write out a sentence. He's running at 5.75. If you can't write a sentence because you're actually not sure the context of what you just solved, then just put the answer and box it and hope that the person doesn't care. That would be a hard question for the diploma exam. That's actually quite similar to one of the ones they had in the past. And it's hard for 2 reasons. 1, it's a word problem, which just freaks people out. 2, it's hard because you're solving a quadratic that can't be factored. Right? And anytime you're having to solve a quadratic that can't be factored is a challenging moment. I believe if they were to break this down, marking-wise, this would be 1 mark. So getting it to the quadratic stage. And then all of this would be a 2nd mark. That's how I suspect they would break it down for you. So if you're wondering what grades look like. I know I've preached it all year when it comes to tests. On a written response question, don't leave it blank. Take a stab at it. right? Even if you demonstrate just the slightest bit of mathematical knowledge that would make sense for this question, they're going to give you a mark somewhere. Maybe just a half mark, but a half mark beats 0 by a long shot. So do something. And in the past, our classes and our school has done a good job of not just leaving questions blank. It goes a long way. Part marks add up. Awesome. This word problem. This is one of the word problems where they've set it up kind of funny. If this was a test question, I actually would expect them not to put anything there. Okay, they would only give you the words, that weird little box setup, and then some more words. I've given you the equation so that you have it in case you weren't here. But we're going to talk about if you didn't have the equation, what you would do. So I'm going to read the question because that's obviously where you always start for a word problem. It says, over a distance of 800 kilometers, the average speed of a small airplane is 6 times faster than the speed of a train. This information is shown in the table below. Reading this table, I have a train. That train has traveled a distance of 800 kilometers. That train is traveling at a speed of X. We don't know it. That train traveled for a time of 800 divided by X. You'll notice that that's your distance divided by your velocity. Right? They're connecting the info for you. Then they give you info about an airplane. An airplane also traveled a distance of 800. An airplane traveled a speed of 6x. That means 6 times faster than the train was going. That airplane traveled for a time of 800 divided by 6x. Again, you'll notice that's d divided by v. Right? All they've done is they've taken all the info from that first couple sentences and they've put it in there. They actually added a little bit because they never told you the distance in the question, I don't think. Oh yeah, over 800 kilometers. That's all they've done. They've organized the info for you in the distance, speed, and time. Realistically, the only thing that probably is going to matter to you is the time column. Because almost all these word problems comes down to time. Right? They're going to say the time of this was that. It took them this amount of time. The difference in time was. But somehow they're probably going to relate the time. So all the other stuff pretty much will be irrelevant most of the time. Okay, let's continue reading the question. We're going to pretend we don't know the formula. And we're going to see if we could put the formula together. Again, there's no question. No question to this question. It says, to travel 800 kilometers, the train requires 8 more hours than the airplane. The equation below shows this relationship. I'm going to say, how fast is the airplane traveling? Man, I'm bad at making questions. 2 questions in a row with no question. Okay, let's pretend for a second that they didn't give us this equation. Because that's very realistic. They give you all that info, and then that's it. They say, how fast the airplane traveled. The key comes from wherever they talked about time. In this question, they said, the train requires 8 more hours than the airplane. All right, that means if you took the amount of time that the train traveled for and you subtracted the amount of time that the airplane was going for, it would be 8 hours, right? 8 more. You could also, if somebody wanted, take the time that the airplane travels, add 8 hours, and it would equal the time that the train traveled. So there's actually multiple things you could set up here. But somehow you have to incorporate that 8 hours and the time in which they both took to travel. In your diagram is the time, or not your diagram, your chart is the 2 times. We have the train time and the airplane time. What I'm going to do is I'm going to take the train's time, which was 800 divided by x. I'm going to subtract the airplane's time, which was 800 over 6x. And I'm going to say the difference between them should have been 8 hours. And that's my formula. They gave that to you already. But that's how they came up with it. They took the time of each thing, they subtracted it, and they said it would be 8 hours. In the past, we've seen the total amount of time that both vehicles travel is 20 hours. That would be time plus time is 20 hours. And so they have different ways that they can phrase it, but you need to just basically be taking these two things and finding out their relationship, how to connect them. Typically for the chart questions, solving them is not that bad. It's the setup that people mess up on. If I have that and I want to solve it, what's the first thing I need to do? Common denominator. I got all monomials here. So this x, I need to be in the second fraction as well. It has an x as a monomial. That's wonderful. Don't forget that 8 is actually 8 divided by 1. So it also needs an x. So I have to times by x, top and bottom. This 6 in the monomial, I need every monomial in the denominator to have that 6. The first one doesn't, so I times by 6. The third one, 8 divided by 1, also needs a 6. So I do to the bottom, I do to the top. You now have a common denominator, which means I can cross out the denominators and expand the top. So 6 times 800. Oh boy, I think I can do that one. 4,800. Everybody go home and watch Rain Man, and then you'll know who I am. The middle one is just 800 because we didn't do anything to it. Equals 8 times x times 6. 8 times 6 is going to be 48x. Once you've got a common denominator and expanded, you should have an equation that you can now solve. Is it linear or quadratic? It's linear. Why is it linear? Yeah, highest exponent's 1. There's no x squared there. Linears are the best ones to solve. The reason they're the best ones to solve is you just have to get x by itself. Right? There's no quadratic formula. There's no factoring. You're literally just isolating x. So to isolate x, I'm going to first combine these two like terms. That will become 4,000 equals 48x. And then I'm going to get the x by itself by dividing by, what did I do? 48. And you should get an answer of x equals, I don't know what it is, less than 10. 83. 83.3 repeated, like that. Awesome. Any questions about the actual solving of that rational expression, rational equation? All right, that is not the answer to the question though. You solve that x equals 83.3 repeated. That's wonderful. The question asked, what is the speed of the airplane, right? How fast is the airplane? The airplane is 6 times x. You solve for the speed of the train, which was x. So if I said, what's the speed of the airplane, you actually have to take your answer and do 6 times that. So for us, we need to do 6 times 83.3 repeated. And that'll tell you the speed of the airplane. What is the speed of the airplane? 500? Exactly?
Yeah.
Beautiful. You don't need to put units. If you put units, kilometers per hour, or whatever the heck the units were, that's wonderful. It's more of a physics issue than a math issue for units. All right, that's rational expressions. In all honesty, there's probably no better unit for a written response question than rational expressions, in my opinion, because it's probably the most algebraically heavy unit. So you can show your work, you can show your steps, and you can actually solve things. So I expect there to often be a written response question that's a rational expression. I mean, that's just an expectation. It doesn't have to be. They could definitely not do one. It just leads itself so nicely that they'll probably keep doing it. Awesome. That's the end of Unit 3. We're going to start Unit 4, which is our polynomials unit. Before we do Unit 4, I believe I have a trivia question. All right, I do. And the answer is not given to you. So remember with these problems, you have a lot of time, right? I would expect you to spend 5+ minutes on every one of these problems before you just give up, okay? And if you do give up on one of these problems on your diploma, go away from it, do the rest of your diploma, come back to it. Because sometimes fresh eyes make these problems so much easier. So I'm going to give you a couple minutes right now just to try it on your own, and then I'll tell you what the answer is. I wasn't going to record solving this, but why not? So first thing I do is I try to read any rules, if there are rules to the question. It says, in a particular game, drawings consist of circles or squares. Okay, so I know there's only two shapes, circles or squares. Different letters are used to describe the type of shape, the number of shapes, and the arrangement of the shape. Okay, so somehow the letters are telling me the type of shape, how many shapes, and the way that they're shaped, like in arrangement. 5 drawings from a particular game are shown below. Based on the drawings above, which of the following statements about the letter A is true? Okay. I'm actually not going to look at any of the answers. What I'm going to do instead is I'm going to try to do the game on my own and figure out what letter A is telling me in this game. Kind of like when we did those Sudoku one, right? Where it was like, find the mistake that someone made. I just did the game on my own and then connected my answer to the answer. And I think that's the best way to do most math questions. And ignore the multiple choice solutions. Do it on your own. See what you get. See if it matches up. If it doesn't match up, do it again. Looking at this, I want to try to compare what stays the same and what changes from game to game. When I look at the first thing, I have a C, a D, a E. I have circles. There's 3 of them, and they're not overlapping. They're like spaced out. If I look at the second one, I notice that it also has a C, but it doesn't have a D or an E. It has A and F. So the only thing that stayed the same from picture 1 to picture 2 was the letter C. Now if I look at the picture, what stayed the same in the pictures? The shape, right? They're both circles still, but I've gone down to 2 things and they're now on top of each other. So I could probably assume right now, C tells me my shape is circles. If I look at picture 3, I'm actually going to try to color code this a little bit better. I'm going to color C in blue. Yeah, watch this. D is going to be red. E is going to be green. A is going to be straight purple. And F will be orange. So if I look at the third picture, I have B, which is a brand new thing for us. We haven't seen that before. I have D, which I have seen before. And I have F. When I try to compare that picture to previous pictures, for instance, the one that both had D, things that stayed the same between the first picture and the third picture. They both have D in common. The number of shapes is not the same. The shape itself is not the same. However, their spacing is the same. So my guess, and just for now, is that D tells me that we don't overlap. And I might be wrong. But that's my first initial kind of suspect now. The other thing I notice is F. F is the same between the second picture and the third picture. So I'm going to try to figure out what's the same between the second and the third picture. Well, the shape is different. The spacing is different. But this thing that's the same between the second and the third would be the number of shapes. So my guess is that F tells me that I have 2 shapes. All right, let's look at the third one. We have A, we have B, and we have E. All things that we haven't decided what they mean yet. Let's compare A with the other A that we have. So the second and the fourth shape both have A's. The thing that's the same between the second and the fourth shape, the number of them is not the same. The shape itself is not the same. However, they are overlapping. So my guess is that A tells me to overlap. If I look at B, the letter B is in both the third and the fourth shape. The thing that they share is that they're both squares. The number of them is different. The overlap is different. So my guess is B means square. If I look at E, E is in the first and the fourth shape. The only thing that's the same between the first and the fourth shape is that there's 3 things. So my guess is E equals 3 shapes. And now I believe I've done all the letters, A, B, C, D, E, and F. That means if I'm right, the 5th shape should follow my rules. A, C, E. A means I should overlap. C, I said, would be circles. E, I said, would be 3 shapes. If I look at my picture, I have overlapping circles, and there's 3 of them. So my rules are all correct. That means I can now answer the question. A represents overlapping shapes. C is the answer. Honestly, you could probably do that question way faster if you just focused in on A, and that's okay. But if that was maybe, say, a numerical response, which was like, here's the rules, which one is A, which one is B, which one is C, which one is D, then you'd have to be able to do that whole breakdown like we just did anyway. So for any game question like that, honestly, that's how I attack it. I try to do the whole thing. It might be more time consuming than you would want, but you're supposed to spend a good amount of time on every one of these games. So it's okay that you're spending a little bit too much time. Cool. Let's get into Unit 4. So Unit 4 is polynomials / sinusoidals. We kind of do both. We're going to start off with remembering some definitions. The word degree. What does degree mean? Yeah. Degree equals highest exponent. Or it means the temperature outside. Right? No? Minus 40 million. Right? Things that have degree 0. Degree 0 is just called a constant for us. You don't see degree 0 very often. An example of degree 0 would be y equals 2. Right? It's just y equals a number, nothing else to it. I could do y equals 1/4. Right? That's a constant. Y equals 0.2. Constant. There's no x's at all. That means the highest exponent on an x is 0. It doesn't exist. Polynomial functions that are degree 1 means the highest exponent is 1. We already know the name of that. We call that linear. Right? What we just talked about last unit. Linear equations have an exponent of 1. The way linear exponents work, they could look like this. Y equals x. That's the highest exponent is 1. You're more likely to see something like this, y equals 2x plus 5. That's a little more common, right? So there is a linear term, meaning x to the power 1, and there's a constant term, meaning that there's no x attached to it. You could also do this with fractions, so you could have something like this, 1 over 2x minus 0.3. Right? That's still linear because the highest exponent is 1. You learned linear equations heavily in grade 10. Degree 2 means highest exponent 2. That would be called a quadratic. Quadratics you learned heavily in grade 11. So a quadratic equation is anything where the highest exponent is 2. A very basic one would be y equals x squared. That counts as a quadratic. You could have a more complex one, which would look like this, y equals x squared plus 3. That's a quadratic because it's got a highest exponent 2. That also has a constant term of 3, meaning there's no x attached to it. Or you could have something like this, y equals 0.5x squared minus 13x plus 9. That's still quadratic because the highest exponent is 2. It just also has a linear term, meaning x to the power 1, and a constant term, meaning no x's. That was heavily done in grade 11. Grade 12, we started doing degree 3. Degree 3 we called cubic. That means you have y x cubed somewhere in your question. Again, it could look more complex. It could look like this, x cubed minus x plus 1. Right? That would still be cubic because the highest is a cube. You could also write it like this, y equals x squared minus 2x plus x cubed minus 5, which would be a crazy way to write a cubic, but it's still cubic because the highest exponent is 3. It just also has a quadratic term, meaning x squared, a linear term, meaning x, and a constant, meaning no x. Fantastic. Things I'd want to know, the word degree has popped up in the past. So degree means highest exponent. And then just those words, cubic, quadratic, linear, constant, probably all good things to know. A nice little overview of what these charts look like. So if you remember when we did this unit, we spent a long time like graphing things in our calculator to see what they look like. We did some experiments, we moved some numbers to see what happens. But at the end of the day, we came up with all this information in a nice chart. If you had everything on this chart memorized, that would be fantastic. Do you need to have it all memorized? No, you could probably just figure it out if you remember what the graphs look like. A constant graph always is left to right. That's it. It's not going up, it's not going down, it's just left to right. It's nice and boring. It looks like this. Those things will always have one y-intercept and no x-intercepts. Unless your constant value is 0 and then your horizontal line is on the x-axis. And then you have infinite of them. It's not going to happen. You're probably not going to get tested on constants at all. End behavior, something we haven't seen in a while. So end behavior is what we do is with arrows. We say what's the left, and I call it tail. And then we draw an arrow. And then we say right tail. So for a constant, we would say it's going from 1 to 2, or sorry, from 2 to 1, or from 3 to 4. And we would just use numerals, Roman numerals, not numericals. Yeah, we'd use Roman numerals, and we just use an arrow. So for instance, I could say that this is 2 to 1. Like that. Domain, it's been a little while since we've done domain. So domain for every one of these graphs, as long as it's not a word problem, will be XER. But please take a note at how it's written. You do need to write with that format. So the format is curly bracket, X, then this line. And then you write any restrictions you have. On your domain, there's no restrictions. You say XER. And then you close the curly bracket. Right? Good. For the range, you follow the same format. You go curly bracket, Y such that. And then you put your restrictions. For a constant, you just say what the constant is. You say Y equals 2. And then you could put YER as well and close the curly brackets if you wanted to. Number of turning points. Turning points are when it changes direction. So it either goes from up to down or down to up. On a constant graph, there is no turning point. It's just always horizontal. Awesome. Linear equations. Linear equations always look like this. Okay, so they're either always going up or they're always going down. That means neither one of those would have a turning point, right? It just makes a straight line. When we talk about linears, they always have one y-intercept and one x-intercept, always. When we talk about their end behavior, they're either going from 3 to 1 or 2 to 4, always. Their domain is XER because you go forever to the left, forever to the right. You have every x value covered. The range is always YER because you're always going forever up, forever down. Right? If you look at both these graphs, this one goes forever down that way, forever up that way. So every y value would be covered. The other one goes forever up that way, so every positive y is covered, and forever down that way, so every down is covered. And the number of turning points is still 0. Number 3, quadratics. Now we're starting to get into graphs that we might actually have to deal with. So quadratics. Always make that shape. That shape is called a parabola. I don't know if you'll need to know that word, but it probably wouldn't hurt. Okay, so that's a parabola. I think that's how you spell it. I'm not an English teacher. I'm just kidding. That's how you spell it. So they always make that shape. Sometimes they open up. Sometimes they open down. Right? If you're never sure, like if you gave you an equation, they said, does it open up or open down? Graph it and figure it out. See if it looks upwards or downwards. If you remember, the A value tells you. Right? A positive A value makes a happy smiley face because it's positive. So this would be a positive A value. See, smiley face. It's positive. It's happy. A negative A value makes a sad face. Right? So sad face. It's going down. Right? And that's how you can tell if your graph's going to open upwards or downwards. Please don't write on your test that it makes a happy smiley face. I might lose my job. Like, what is this guy teaching? Happy smiley face. Like it doesn't that work though? It does work. It makes a little smiley face. Positive, happy. Negative, Eeyore. Damn. Negative, Eeyore. When it comes to x and y intercepts, they can be deceiving. All right, we'll talk about y. Let's talk about x-intercepts first. There's 3 different possibilities. So depending on where your parabola is, it could possibly have 2 x-intercepts, like this blue one has 2 x-intercepts. It could possibly have 1 x-intercept if the vertex touches the x-intercept, like that one. Or it could possibly have no x-intercepts, like that green one. It never actually goes low enough to touch the x-intercept. So all 3 situations are possible, just depends on the quadratic. Y-intercepts can be deceiving. The reason the y-intercept can be deceiving is if you look at the green one in particular, The green one looks like it has no y-intercepts, right? It doesn't touch the y-intercept. In fact, it's not even close to the y-axis. So it doesn't look at all like it's going to touch it. However, with quadratics, when it's going forever up or forever down, notice that it's on a slight angle. So that means it's actually going forever to the left as well. So if I could go high enough, that graph would go far enough left to have a y-intercept at some point. That means every quadratic has a y-intercept somewhere. Even if when you graph it, it looks like it doesn't. The end behavior, please make sure that you think about the graph going forever left, forever right. So for instance, with the blue graph, the end behavior looks like the left tail is here. Looks like it's in quadrant 2. And the right tail looks like it's also in quadrant 2. But if I kept going, which quadrant would it eventually end up in? Yeah, it would eventually end up in 1. So the end behavior is actually 2 to 1. Don't say 2 to 2. Okay, you should always end up one of the left quadrants, one of the right quadrants when you're doing your end behavior. The green one kind of falls for the same trick. The left tail is in quadrant 1 right now, but which one would it end up in if you kept going? Yeah, it would eventually go to 2. And it would end in quadrant 1. So left tail to right tail. And that's how you read it, right? Left to right, like a piece of paper or a book. I can't read books, but if you could, you read left to right. Unless you're reading Japanese books, then it's right to left and backwards. Yeah. What is it called? Manga? 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 Not manja. It's an English boy trying to speak a word that's not English. Manga? So manga comic, it's like Japanese comic books, and you actually read them backwards, like from the back to the front. And you read right to left. Mm-hmm. I know Miss Milky has some. The library has a bunch. Mr. Hart might have some. If you ever want to see one. Yeah, it's kind of cool actually. Reading a book backwards, you think they're nuts. Yeah. Like, what are you doing? You've seen a lot of parabolas, right? So parabolas happen all through grade 11. We've talked about everything. The only thing that's tricky is usually the range. The range is different because there is a maximum or a minimum value. So for instance, let's look up at these graphs. If I wanted to do the range of this blue one, I would say that the y values, the y values have to be greater than or equal to this point right here. Right? It could be anything above that. So I would actually have to find with my calculator what that point is. We call that a vertex. More specifically, we call that a minimum value, which with your calculator you should be able to do. It's second trace minimum when you graph it, and you can find where that value actually is. And my range would be y is greater than that value. If you look at the red one has a maximum value. It has a highest point it ever goes. That means y should be less than or equal to that maximum value. So your range is a little tricky for quadratics. Beautiful. Cubics make these cool patterns, typically the green one or the red one, where they have like 2 bumps, right? It goes down, up, down, and it makes that pattern. It could also go up, down, up, but it has those 2 different changes in it. It is possible that those 2 bumps like collide to become 1 bump, and it looks like the blue one that we have over here. Right? Like if you look at that, there are no actual bumps. That's because they've kind of combined into one, and they make this point of inflection where they go up, they go flat, and then they keep going up. It never goes down. It's called a point of inflection. If you are somebody who knows that that's not actually what it's called, and I'm wrong, please don't make fun of me in the comments on the YouTube video. It hurts my feelings. That guy who did that last time.
Oh,
Yeah, he said I was wrong. Remember that? Oh, it hurt my heart. So just mind your own business, smart people. But I'm pretty sure it's called a point of inflection. You hopefully never need to know that because, yeah, we're going to stick with that. If that ever happens, just pretend you know what you're talking about like I do. All right. Yeah. My teacher said it's a point of inflection. He also said he's not sure. Sorry. Like, put that on the wall. His name is, and he works at. Yeah. Call his personal cell phone at 403. No, don't call me. Ever. Ever. When it comes to x-intercepts, you could get a wide range. You'll always at least have one. Okay, but then you could possibly have two. You could possibly have three, just depending on where those changes are. Right? If you look at the green one, that one has two. There's one here and one here. The red one has three. There's an x-intercept here, here, and here. The blue one only has one, right there. So it all just depends on the graph. If you have to find the x-intercepts on a graph, it can be tricky. Just remember what a cubic should look like. And make sure that on your graph, you can see that shape somewhere. It's probably the biggest. The y-intercepts, again, it always has one. The end behavior, I don't think we need to talk about. XER, YER for domain and range because it goes forever left, forever right, forever up, forever down. Number of turning points is either 0 or 2. A point of inflection does not count as a turning point because it never changes direction. It goes flat and then continues on the direction that it was going. So please don't say that a point of inflection is a turning point. Not that I think you would. Cool. Let's do word problems. That's pretty much what this whole unit came into. Right? It all basically ended up as word problems and or ended up as us having to create equations in our calculator and do regressions. That's basically the whole unit by the time we were done it. We'll read example 1. It says the height of a rock being thrown from a tree fort can be modeled using the equation. Then they gave me an equation where t is greater than 0, where h is the rock's height in meters and t is the time in seconds. When it comes to word problems like this, I think it is very wise to, on the side of your paper, write what each thing means. So h is the rock's height. I'm going to write on the side h equals height. Then it says t is time. T equals time. The reason I do that is sometimes they use weird letters, right? And then it's like, oh, I don't know what P was. P was height. Like, why would it be height? But you need to know that. Or they'll put like the letter X and they say X is the length of a side. And you're like, well, I don't know that X is side. And that little like time to write on the side or in the margins of your test could save you and remind you of what's what. Question A, what is the maximum height of the rock? When it comes to questions like this, anytime you see maximum or minimum, you're going to have to graph it. We have no way to algebraically calculate the maximum or the minimum. Well, we do, you just haven't learned it before. But for us, we just use our calculators. That means we're going to have to graph this thing. To graph it in your calculator, you go y equals. So in the top left-hand corner, you have a y equals button. You hit y equals. In y1, you're going to put in that equation. You don't have the letter t, so you're going to have to put x. So you should now have in your calculator y1 equals negative 4.9x squared. If you don't remember where x is, hopefully you left your x far, far away. It's better that way. Or, hey, thanks. I got 3 smiles. So the x button on your calculator is right beside alpha. So alpha right here, there's these 4 symbols. That's x. And then you go plus 100. I trust that you all have that now in. Before you graph it, you always want to set a window. And that's typically the hardest part of our word problems is setting the window. If you don't set the window properly, it makes it pretty much impossible. When it comes to the cubic questions especially, or the sinusoidals, if you can't set a window, zoom fit typically doesn't work anymore. So you need to understand what your window is asking. So go window. The first thing on window is x minimum. For us, x was t. T meant time. We're talking about a rock getting thrown from a tree fort. What's the least amount of time a rock could be thrown in a tree fort? 0. So your x minimum should be 0. X maximum. That's the maximum amount of time that the rock could be in the air after you threw it from a tree fort. Now, even if you had a good arm and you threw that thing pretty high up in the air, maybe your tree fort's pretty high up in the air, I don't expect a rock to be in the air for more than what? 20 seconds? That'd be a long time. That's a high tree and I chucked it pretty high up. If you just ballpark it, like 20 is a good ballpark, it might be too big, it might be too small, but it should be a good enough value to see your graph when you first graph it. And then you can always adjust your graph after. So I'm going to say x max equals 20 is wonderful. X scale, that's what your graph's going to count by. I just always leave it at 1 because I'm too lazy to explain it or wanting to confuse you. Y minimum. Your y value in this case is height. The minimum height that a rock could be at is 0. That's when it's hit the ground. Right? Height off the ground, 0. Y maximum. All right. Now, you could try to use context to do this, but it's hard because you don't know how big a tree fort is. So you don't know how high off the ground this thing really, really could be. There is a good way to get a hint from it. If you look at your equation, remember that your constant term, the term with no letter, is your y-intercept. So that gives you a hint of where you started. Our y-intercept in this case would be the height of my tree fort. I'm 100 meters up in the air. That's a wicked tree fort, by the way. 100 meter up tree fort? Very realistic question. So if I'm already 100 meters up in the air, that means my y maximum should be bigger than 100 because I probably threw it up at least a little bit. So I'm going to say like 110 meters. That might be too high, but that'll be fine. It'll work for me. If I go y scale equals 1, I can now graph it. So 0, 20, 1, 0, 110, and 1. And then hit graph. My graph looks like this. I have a y-axis, an x-axis, and my graph goes like this. What that tells me is that my x value is too big. Right? I have all this wasted space over here. So what I could do is if I wanted to view this a little nicer, I could change my x value to be a smaller number. Instead of 20, it looks like I could probably make it 5, and that would be pretty good. So I'm going to try again, but with my x maximum at 5. And now I should probably see my graph a little nicer. I still have my x-axis and my y-axis, but now it looks like this. A little bit better, right? I filled my calculator screen a little nicer. Your goal was to find the maximum height of this rock. To find its maximum, you're going to go second, trace, second is here, trace is above the top, and the word maximum is your fourth option, maximum. And now your calculator says left bound, right bound. What you want to do is you want to use your left and right arrows to move your little cursor so it's left of the maximum. So I'm going to hit my left arrows until my cursor is past this lump. Right? And I can go off the screen if I need to. So I'm actually going to go left right off the screen so I'm past my maximum. I don't like this question. That's okay. Yeah, probably. At least it's a question this time, not a statement like the last two word problems did. And then I hit enter, and it says right bound. Now your calculator wants to go right of your maximum. So using my right arrow only, I go right of my maximum, and then I hit enter. And I hit enter one more time, and it tells me that my maximum is at Negative 1.211 E.
Would.
And you might have a different number, but do you have an E?
Yeah.
E means 0. So the maximum is at 0, comma 100. That means the maximum height is actually at the tree fort height when I threw the rock down. So my maximum height was 100.